Maybe the best accomplishment of late 20th and mid-21st century astronomy is the appearance of an agreement model of the whole universe, lambda CDM cosmology. For endless ages, people have wondered about questions such as what the universe is made of, how far it extends, how it appeared, how long ago, how it evolved to be what it is today, and what its ultimate fate will be. Today, after exceptional measurements of galaxies throughout cosmic history, all-sky imaging of the universe at microwave frequencies, and thousands of supernovae and other transient events across the universe, we finally have answers to these inquiries. Our universe, made of 68% dark energy, 27% dark matter, and just 5% ordinary matter, began from a small, dense, nearly uniform state some 13.8 billion years ago in a hot Big Bang and has been expanding, cooling, and evolving ever since. Essentially, that is the consensus picture. But now, the James Webb Space Telescope, with its exceptional infrared capabilities, has been challenging what we assumed we knew about the early universe. Rather than showing the formation of just a few small stars, which would satisfy the timeline of the hierarchical structure formation theory, the telescope is now sending back data that presents serious challenges to current creation myths. As it looked deeper into space, the telescope revealed phenomena that challenged long-held assumptions about the origin and development of the universe and shed new light on significant scientific and philosophical questions. Indeed, the galaxies captured by James Webb existed far earlier than anyone had expected. In other words, somehow the universe is building galaxies earlier and faster than our theories predict. This was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Another way to imagine it is like going to a nursery to visit your newborn and finding a room full of teenagers, which is truly unsettling, to say the least. So, what does this mean for the history of the universe? Frankly, Webb's revelation could have significant implications for cosmology, as it suggests that current theories about the formation and evolution of galaxies could be wrong or inadequate to explain the existence of these galaxies. Scientists may need to revise models of the universe's evolution and galaxy formation processes. One possibility is that these massive galaxies formed differently from the galaxies closer to us. For instance, there may have been an unknown mechanism until now that allowed for the formation of giant galaxies in a short period of time. Another possibility is that these galaxies are the result of unusually rapid mergers between smaller galaxies in the early universe, which would also require a revision of current models. In any case, the discovery made by the James Webb Space Telescope represents a significant advance in the study of cosmic evolution and galaxy formation. This finding is likely to prompt astronomers to develop new theoretical models and seek more observational evidence to better understand the history of the universe and the properties of these mysterious distant galaxies. But note that the impossibly massive galaxies were not an isolated incident. Cosmologists have long thought that brand new galaxies that started forming soon after the Big Bang, around 13.7 billion years ago, were too fragile to exhibit any noticeable structures like spiral arms, bars, or rings. These cosmic features were believed to form during a period about 6 billion years after the Big Bang. However, according to a new remarkable study made by James Webb, these delicate shapes may have appeared as early as 3.7 billion years after the Big Bang, which is nearly at the beginning of the universe. As Christopher Consolis, an astronomy professor at the University of Manchester in the UK, and a co-author of the new study said in a statement, "Based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years. These findings come on the heels of another announcement presented by a different group of researchers, based on Webb's data, which showed that these early galaxies produced far fewer heavy elements than previously anticipated. However, the relationship between a galaxy's chemical composition and its development into a distinct structure is not well understood. Much of scientists' previous understanding of galaxy evolution came from data gathered by the Hubble Space Telescope, which is remarkable in its own right but still has only so much resolution. While Hubble's data showed early galaxies had irregular shapes, as was expected during galaxy mergers, higher resolution data from James Webb is looking deeper into the universe to reveal that those galaxies actually had well-defined structures, much like our own Milky Way. The new findings were based on an analysis of 36 galaxies, which astronomers say is the largest sample studied so far with Webb's data. In the words of Leonardo Ferreira, an astrophysicist at the University of Victoria in Canada, and the lead author of the new study. For over 30 years, it was believed that these disk galaxies were rare in the early universe due to the expected violent encounters that galaxies go through. The fact that James Webb finds so many is another sign of the power of this instrument, and that the structures of galaxies form earlier in the universe, much sooner, in fact, than anyone had expected. According to the new study, the team cataloged a test set of nearly 4,000 galaxies from the early universe by shape, like disks, point sources, and spheroids. Colleagues further classified them as smooth or structured, with galaxies in the latter group featuring bursts of star formation and signs of mergers with other galaxies. Results showed that well-defined structures in the universe formed a lot quicker than previously thought, following what is known as the Hubble sequence, which is the standard classification of galaxies by their visual properties as ellipticals, lenticulars, and spirals. The latest findings suggest a need for new ideas that explain how galaxies evolved over the past 10 billion years. Elsewhere, there have been other Webb observations in which the evidence behind science's fundamental understanding of the universe has been found alarmingly inconsistent. Take the issue of how fast the universe is expanding. This is a fundamental fact in cosmological science, the so-called Hubble constant, yet scientists have not been able to settle on a number. There are two main ways to calculate it. One involves measurements of the early universe, such as those that Webb is providing, and the other involves measurements of nearby stars in the present-day universe. Despite decades of effort, these two methods continue to yield different answers. At first, scientists expected this discrepancy to resolve as the data got better, but the problem has stubbornly persisted even as the data have become far more precise. Now, new data from Webb have worsened the problem. This trend suggests a flaw in the model, not in the data. It is time to revise the theory of the Big Bang. Perhaps, as Dr. Luke Barnes, a postdoctoral researcher at Western Sydney University, said, "It's more likely that the story of the Big Bang will become part of a larger story." Nicholas Copernicus' model of a sun-centered universe was never overturned per se. Rather, Johannes Kepler refined the planet's orbits, Isaac Newton explained the forces, and modern astronomy has placed our solar system and our universe in expanding space. We can only use observations and theory to peer so far back in time, so for the Big Bang, there is a lot of room for a prequel that explains what happened in the earliest fraction of a second of the life of the universe. Similarly, we can only see so far in space to our cosmic horizon. The universe beyond could have similar properties as our own, or we could be part of a vast and varied multiverse. But as before, to start a cosmic revolution, you must do it right. We all know that there are some problems with the Big Bang theory. Since scientists first proposed the Big Bang theory, many people have questioned and criticized the model. Here is a rundown of some of the most common criticisms of the Big Bang theory. First, it violates the first law of thermodynamics, which states that you can't create or destroy matter or energy. Critics claim that the Big Bang theory suggests the universe started out of nothing. Defenders of the Big Bang theory say that such criticism is unwarranted for several reasons. The first is that the Big Bang doesn't address the creation of the universe but rather its evolution. The other reason is that since the laws of physics break down as you approach the creation of the universe, there's no reason to believe the first law of thermodynamics would apply. Second, some critics say that the formation of stars and galaxies violates the law of entropy, which suggests systems change to become less organized over time. However, if you view the early universe as completely homogeneous and isotropic, then the current universe shows signs of obeying the law of entropy. Third, some astrophysicists and cosmologists argue that scientists have misunderstood evidence like the redshift of celestial bodies and the cosmic microwave background radiation. Some point to the absence of certain cosmic bodies that should have been the result of the Big Bang according to the theory. Fourth, the early inflationary period of the Big Bang seems to violate the principle that nothing can travel faster than the speed of light. Defenders have several responses to this criticism. One is that at the start of the Big Bang, the theory of relativity didn't apply, so there was no issue with traveling faster than the speed of light. Another related response is that space itself can expand faster than the speed of light, as space falls outside the realm of the theory of gravity. There are several alternative models that attempt to explain the evolution of the universe, but none of them have as wide acceptance as the Big Bang theory. For example, the steady-state theory proposes that the universe always looks the same and continues to look the same forever. As the universe expands, new matter forms to maintain the density. The Big Bounce theory uses recurring periods of contraction and expansion. According to this theory, our universe is just the latest in a series of universes that have formed over the course of billions of years. The theory relies on some concepts from quantum physics, such as loop quantum gravity. The last of the major rival theories is the plasma universe theory, which proposes that much of the behavior of the universe is due to electromagnetic forces rather than gravity. For decades, physicists have attempted to unify the study of the universe under a single theory, and recent discoveries and measurements suggest that they may need to do so again. That unifying idea would need to explain several thorny observations, such as the motions of stars and galaxies, the rapid expansion of the universe, and the mysterious nature of dark matter and dark energy. Of course, the potential breakthrough on all of these questions could come from James Webb itself, just as Webb raised these questions in the first place.